Hi, my name is Marshall Ward, and I'm a member of the Ocean and Cryosphere group at NOAA GFDL, where I work on development of the MOM6 ocean model. And today I'm going to be talking about some of the techniques we've started to adopt for evaluating the computational performance of the model, especially with respect to a potential peak performance for the algorithms within it. So in this video, I'll talk about what I mean by peak performance, and I'll go over how one might estimate said peak performance for a few simple numerical methods, and then I'll wrap up by showing how we are starting to apply the same methods to the MOM6 code itself and how they have helped guide our own efforts to optimize the model. So before getting into peak performance of a particular numerical method, let's start with a baseline for the hardware that we might run them on. Here I've shown the two platforms that we're going to be looking at. One is a x86 Intel Cascade Lake CPU, and the other is a NVIDIA Volta GPU architecture. And the peak performance of these machines would be defined as the work capable of the cores within them times the number of available cores, and then finally by the speed or clock cycles of those cores. Core can itself be a bit of a soft definition, particularly when we try to compare them across these two types of architectures. But if we just sort of take it as the minimum unit of work, then we can do this calculation. And I do not have time to explain where these numbers come from, but if you take them, they do represent the very best that these could do under very ideal circumstances. And so this middle column shows that theoretical value if you just multiply cores by work per core and the speed of them. And both numbers are very high. You can see that the CPU can do over 2 teraflops, whereas the GPU can do over 7. And these are numbers we can replicate if we just fire up all the registers on them. But do they reflect actual practical work that could be achieved? And I would say yes, under the right circumstances. This figure is showing a matrix calculation, which does take the most advantage of that hardware. And you can see that both do eventually get to that peak value indicated by the dash line on here. The blue is the Intel architecture and the orange is the NVIDIA. And the x-axis here represents the number of elements in the calculation. So if n is the dimension of the matrix, this x-axis would be something proportional to n squared, whereas the y-axis here would be the gigaflops per second. And so both do, once the problem gets large enough, both do start to asymptote towards that peak value. But that only is really reflective of a certain class of problems. If we were to instead look at a typical array update, we wouldn't get anywhere close to those peaks. We would instead see the trends shown here in the green and red. In this case, this is just what's called a simple AXPY calculation, which I'll explain in a minute. But the green indicates the Intel and the red is the NVIDIA. And we see that neither reaches the peak, and instead what we have is a pretty interesting structure to the Intel, where these smaller arrays tend to perform not at the peak, but nonetheless quite well. Whereas once the arrays get large, their performance drops. The GPUs show a pretty different trend, where the smaller arrays have rather poor performance, but once we get up to about a million, they start to approach some sort of peak value, and then at about 10 million or so elements, there's a real transition. So can we understand those trends? Yes, pretty easily. So this is, if we look at the matrix multiplication, it has what we call the arithmetic intensity proportional to its problem size. So as the matrices get larger, the amount of flops we need to do per byte read in increases. In other words, we have more work to do as the problem gets larger. And so it reduces the burden on whatever bandwidths are in the machine and lets us reach that peak performance. The array problem is very different. In this case, the work grows as the array grows. So the bandwidth ultimately dictates the performance. We're not able to ever really reach that peak value. We end up unable to deliver enough data to do the work to take full advantage of the hardware. So that is what arrays work. I would argue, and I think I can make that case implicitly for this audience, that array array calculations are much more reflective of the work we do in oceanography. We tend to do array updates in our hyperbolic solvers. We tend to avoid elliptic solvers where possible through the hydrostatic assumption. And I think that if you look in any sort of Brian Cox style ocean model, you will see mostly array updates. So there is a structure within them where for smaller arrays, as I said, there is this peak, and then for larger, it drops quite sharply on the x86s at least. And what we can see is different expressions of array updates have different peaks and troughs. And what I'm arguing is that we can do an analysis on these expressions to understand those peaks so that we have an expectation on the performance we ought to get based at least on both the expression and the size of the problem we're working on. So if we take those figures in the previous and we throw them on something called a roofline diagram, we can see that yes, the bandwidth does start to explain those trends. So on this figure, instead of on the x-axis, before we had problem size, instead what we now have is this arithmetic intensity, or the flops per byte, or the indication of the capacity of the problem to do work. And what we see is that the values do remain bound between these two diagonal lines, each which indicates the bandwidths of the system. So the lower diagonal line is the bandwidth of the RAM on the external RAM on the machine, and the upper diagonal lines indicate the bandwidths of the caches themselves into the CPUs. So you can see that the performance one is bounded by those two values. It does dip below the RAM a bit on there. We'll explain why when I get to that. But the main feature here is that as the arithmetic intensity is increased, so is the performance. So is the bounds from above and below. And so it does give us the first indication that that arithmetic intensity is an indicator of performance. And if we know those bandwidths, we ought to be able to just multiply it by that AI and just predict at least how we ought to do in the best of circumstances. So without really getting into the details of how cache bandwidths work, I will say that yes, we can estimate them based on the rate of delivery of the L1 caches in our x86 to the computational elements. And if you just take my word for it, we can get a number of about 8.6 terabytes a second, showed as 8600 here. What's not shown here are the bandwidths into the external RAM and to the compute nodes. And what we have are much smaller values. For the x86 Cascade Lake, we have around 140. And for the Volta, we have GPU, we have around 900. The reason I'm not showing the Volta cache speeds is because, as we saw, there really is no direct benefit to that bandwidth. Ultimately, these problems are driven by the RAM bandwidth on the GPUs. But these three numbers ought to give us all the information we need to predict the best possible performance under certain circumstances for our expressions. So let us start with an example. We'll just look at the Euler time step here. It's about the simplest thing we can imagine. It involves reading in two values, multiplying by a time step, and then adding that tendency to the original array, and then saving it back to itself. So you can see it in the equation on the first line and as an example of a code line in the second. And what we can do is count the flops here, which in this case is 2, the multiplication and the addition. And then we have, in this case, 2 loads and a store. So we would say we have 3 data transfers and then 8 bytes per number. So we would get an arithmetic intensity of a 12th. So if we multiply that 1/12 by those bandwidths shown before, we can get estimates for the best possible performance. If we're cache bound, we get a number that is within a sliver of the peak, 99.7 in this case. And that's really shows that yes, this is something we can achieve. This first column are numbers I was able to produce in a benchmarking tool that I've developed. The second and third rows show the bandwidth bounds, and they do not quite reach that theoretical value. They're within 80 and 90%. That is reflecting a known inability of RAM to ever really deliver what is called the burst rate of the RAM. There are architectural challenges to getting values off of RAM and into the CPU itself, and that's what these percentages reflect. But that's really not a reflection of our problem. That's a limitation of the hardware. And this also does explain why those numbers do bleed below that DRAM line in that earlier roofline figure. For this talk, let's just take it as a given that there is this lower bound, but I would say in general, this was a good ability to predict the performance. So let's move on to a slightly more complicated example. This is a 1D diffusion solver. Again, we're keeping it very simple. If we do a little algebraic manipulation here, or our compiler does it for us, we can get this down to 4 flops. And in this case, what we have to do is a two-stage operation. So first we would calculate the right-hand side, and that would involve one read. Even though the X value is spread across 3 stencils, we would assume that our compiler is smart enough to cache those older values so that in the end we only do one read and then we keep the 2 older ones around. Then it has to write to a new array, but because we have to copy it, we have to do the update first, it has to do a second copy back to the original array. So we would say this is 1, 2, 3, 4 loads and stores, and 1, 2, 3, 4 flops. So the arithmetic intensity in this case would be 4 over 32, or 1/8. Now, if we apply those bandwidths, multiply those bandwidths by that 1/8, we do not get the predictions. We get numbers quite a bit lower. In this case, 60% or 70-ish% on the GPU. And so this is a challenge to this. And the question is, can we explain it? And the answer is yes, but we do need to start appealing to the hardware. There is something called the right allocate effect, where when you want to read a value that has to touch the L1 and communicate with RAM, it does need to do an additional read. So what's going on is that in the first Euler example, we were reading to the array that we were updating and then writing back to itself. However, in the second example, we were computing the right-hand side as X and then saving it to an all-new array as Y. That triggers this right allocate effect, and it means that we have to implicitly assume an additional read for every write that we do. If it's not explicit, we have to throw it in and treat it. Now, I will say the GPU does do a better job here. There's some architectural thing going on that lets it require only the equivalent of a half read. I have to assume they're doing something clever with the sharing of data. It may also reflect the embeddedness of the GPU RAM with the solvers. But nonetheless, the effect is there, and it does explain the lower theoretical values for the RAM-bound cases. But it does not help us explain the cache-bound, which does not suffer from this. In order to understand that, we have to look at what's going on. So this is actually a two-stage operation where in the first case, we're computing the right-hand side and saving it. And if you look in this first line, the AI is doing a wonderful job of predicting. We get an over 98% of the peak. And the copy is 80%, which is not peak, but it's still pretty good, particularly understanding that copies are a challenge. But finally, when we combine those steps together, we get the 60%, which is nowhere near the individuals. And what that is showing is that there is a cost to changing what we do. So if we keep changing what we're doing in our code, and we keep doing a different array update, there's a spin-up time where we have to get up to the size of a big enough array to capture those peak values. So that's reflecting why we're getting this 60% inefficiency. So just quickly moving on for the sake of time, let's finally try to evaluate these principles to Mom6 output. So I'm going to run what is a very simple benchmark explanation. I'm not going to go into detail here. If you want to read it, you can. But it's meant to represent about 1 MPI, typical MPI domain per core in either the x86 or the GPU. But that is what we're looking at. And so we can calculate the flop rates and the time in the individual subroutines with some confidence. And we might be tempted to say, well, the ones that are very fast are the good ones and the ones that are very slow are the bad ones. But it really doesn't properly reflect that different functions are going to have different AIs, and we should have different expectations for them. So in order to do that, I've taken all those functions and instead thrown them on this roofline diagram here, where we see these two dots on the right indicate the two fast ones. And the reason they're fast is they have high arithmetic intensities, whereas the slower ones on the right-hand side have low arithmetic intensities. So in fact, they're really following this trend that we've been describing, where low AI has low performance and high AI has high performance. But in fact, I want to call attention to these 2 points here where we have done a specific effort to optimize those. And what we've done is move those upward. And so even though they represent slower functions in the overall model, we've been able to target those because they were so low and move them up. And just for an example of the speed ups here, we're talking about a 2x speed up. So um, they have been able to capture what we want to see. So we feel like those diagrams are giving us a real potential path to identifying how fast we ought to do for those functions. And I feel like most ocean models, given that they are bandwidth limited, the AI is proving an effective tool for predicting not only how we ought to do, but also targeting where we go. And I put some comments here about expectation for CPU and GPU that might be better for the discussion. So I'm going to leave it there, and I hope that we can discuss more during the meeting. Thank you for listening to my video.